a certain airline's regulation that the sum of the length, width, and depth of a certain piece of carry-on luggage must not exceed 100 centimeters. So we're going to start a lot of these questions. It's helpful to draw your picture of what you're dealing with. So there we go. I better put a handle on it. There we go. There's the handle for your luggage. Okay. Ooh, it's a blue piece of luggage with a green zipper. There we go. So fancy. Okay. Now, it says that several carry-on luggages have a length of 10 centimeters greater than their depth. So what we have here is we have to introduce a variable because we don't know what the depth is. So we can say that this could be x, and then this side has to be x plus 10. And we want to find a volume. What is the other length that we need? We've got the height, or the depth of it. We've got the length. We'll need the width. What number would go in here? Or what variables could I go in there? One of the best ways to figure this out is to think in real numbers. So if x is 20, 2 centimeters would be like, we could do 2. But if it's 20 centimeters, how much is this? 30. And what would the question mark be to still be the biggest possible, but still fit? 50. Good. So with real numbers, you could figure out what should go on that question mark side. Now, if this was change a different number, let's go with Kino saying it's 2. I like super skinny suitcases. Then this would be 12. How much would be left for the width? 86. Okay. So now let's figure out the blue. Now that you've thought about it with numbers, you can probably think about it with algebra. How are we getting which? The 2 and the 20 were arbitrarily just picked. So the ones on the right is because it cannot exceed 100 centimeters. So that would be the biggest it could be. Well, if I have 20 here and 30 here, I've used up 50 centimeters. The most that I could have left is 50 more. If I did 2 here, 10 more would be 12 here. The most I could have left is 86. So now we're going to think in the blue with the algebra, if I've used up x there and x plus 10 there, how much is left? 100 minus 2x's minus 10, which you could simplify to just be 90 minus 2x. Well, you could factor it if you'd like to, but that would be... No, that wouldn't be the same. Because look, if I do 45, if my x is 20, 45 minus x gives me 25, and I want it to be 50. So write a polynomial function to represent the volume. Now the volume is length times width times height, so we have an x times an x plus 10 times a 90 minus 2x. And we want to graph this function. Why is this easy to graph? Because it's already factored. It's already factored, so you know that the zeros are x equals 0, x equals negative 10, and x equals 45. So if I wanted to sketch a graph of this, I would know the following. I know that I have an x-intercept at 0, 1 at negative 10, and 1 at 45. Since I have 1 at 0, that would be my y-intercept as well. What kind of graph is this? What kind of end behavior will it have? Is it an x squared graph, an x cubed, x to 4, x to 5? It's an x cubed graph. Is it a positive x cubed graph or a negative x cubed graph? It will be, if you do the x times the negative 2, you'd get negative 2x cubed. And so its end behavior acts like a line with a negative slope. So when I go to graph it, I know that it's going to start up here, go straight through, arrowheads on the end. And so now we have a sketch of our graph. Yes? We do know the y-intercept. You could plug in 0 for x, it's going to be 0 right there. If it wasn't at 0, you'd plug in 0 for x into your equation. So I'd have 0 times 10 times 90, which still ends up being 0, but you have to plug in 0 for x. Okay. Yes?
Will it ever ask you to, like, graph it, like, accurately with a calculator?
This would be accurate enough without a calculator. Okay, so this could go up super high or not. So we're going to label our axes. This, in this case, is our volume, and this is our x, which happens to be our depth.
How do you know that?
Because of our equation, right? We have a y-axis and an x-axis, right? But we had v equals, so instead of y, we have v, and v stood for volume. And this is my x-axis, and I have to say, well, what did my x stand for? If I look at my picture, I can see that x was my depth. Now, this is the complete graph. However, in a real-life situation, certain numbers don't make sense. For example, why does it not make sense to have a depth of 50? What would this side be if I chose 50? 60. And then what would this side have to be to make 100? Negative 10, right? I love those suitcases with a negative 10 centimeters. Right? It's like a black hole. You can just fill it up forever. Okay? So it doesn't make sense for 50. Okay? It also doesn't make sense to start off with a negative number. So in our graph, I'm going to take out my highlighter, and I'm going to say, does it make sense that only this part actually works? Your depth has to be somewhere between 0 and 45. 0 itself doesn't make sense. Neither does 45. But anything else could be possible, although you probably wouldn't like a suitcase with a depth of 1 centimeter. But I guess it could be possible.
So 0 and 45 are possible because y is 0?
Well, if you put 0 in for your depth, can you imagine a suitcase that has 0 centimeters for depth? If you put 45, if I put in 45, then this side is 45, this side is 55, and that already adds up to 100, so then that side would be 0. Also problematic.
Should she open that?
What's that? So 0 and 45, if you want to be really specific, would be open dots, yes.
Like on the exam, it's going to do that? That's not how it's all?
Nope. They would, on the exam, what they would do is they'd say, okay, well, we would want to know that you could graph it and understand that that's the part that's only possible. Now, this question would be a calculator question because we want to find the maximum volume. Now, on a cubic graph, it goes up forever, but since these values don't make sense, we're really looking for that value right there. So what our job is right now is to take our equation and put it into our calculator and see if we can get this graph to show up on our calculator. In particular, we want to see this window So we take out our calculator. And we type in our equation, x plus 10, 90 minus 2x. And if you go to graph it initially, this is probably what shows up. Okay? Well, for one, if I want to see this window, can you see that my x values go up to 45? So one of the things you can do on your window is say, I need to see maybe from -5 up to 45. So you start with that and hit graph, and then you're like, Wait for it. Wait for it. It's thinking. Oh, there it goes. Maybe I should go up to 50 because 45 was the x-intercept. It's still going to be problematic. We see a straight line going up at 0, and we see a straight line coming down at 45. There it is. Why is that? Because it goes way up there. And we have to see how high it goes. Now, you could guess and check with your window, saying, I need to go up higher. So what should I try for volume? How high do you want to try next? We're at 10. Want to try 100?
I did 5,000.
You did 5,000.
Yeah, you can see.
Oh, not quite. I can't see the top yet. But it's better. Maybe you did 50,000. So you can guess and check for a long time, or above your graph button is a table button, and what that table button is, it gives you a table of values. If we look at our table of values, you can start to see when x is 1, it's at 968, and you can go down in your table of values, see how it's getting bigger? And you can get a guess at how the maximum is going to be. You could do zoom fit too, but I want you to, sometimes the zoom fit will throw it off completely as well. So we want to have just the window that makes sense. It looks like the biggest it's ever getting is around 30. It's at 36,000. So now I can go to my window and maybe change it to 40,000. And now we can see our maximum. And once we've got that, your calculator has built in to find a maximum number 4. It says pick a value to the left of your maximum, push enter, pick a value to your right of your maximum. So you can either use your arrow key to go past it like this, but if that's taking too long and you know what your scale is, you can also type in a number. So I know that 40 is to the right of it, and that was quicker than using my arrow keys over. Once you've got something on the left and right, it's going to ask you to guess. I think the maximum is going to be there. Push enter again, and it tells us our maximum happens at 28.58. and 36,209. I'm just going to drag that into here. Make it smaller. Because the question asked in the end, what are the dimensions to the nearest tenth of a centimeter? So we know that our depth is 28.6 centimeters. That means our length is 38.6 centimeters, because you would go plus 10. And our width would be whatever's left, subtracting from 100. So if we would do 100 minus 28.6 minus 38.6, it's 32.8. The max volume that you could have is 36,209.9 centimeters cubed. Is that big? How big is that? It's not that big. Have you ever purchased luggage that its capacity was measured in liters? Have you ever seen that? A lot of backpacks are measured in liters. I had a backpack that was an 85-liter backpack. So technically, you could fill it full of 85 liters of water if you wanted to. That would not be very fun to carry around, and it probably would leak. Okay? But here, do you know that 1 centimeter cubed is equal to 1 milliliter? Okay? Have you ever heard of that? 1 centimeter cubed is 1 milliliter? Have you ever got a shot from the nurse and they said, we're going to give you 10 cc's of something? Or when they say cc, they mean cubic centimeters, which is the same as 10 milliliters. So there's some language that maybe makes more sense. Anyways, so if I divide this by 1,000, this would be a 36-liter piece of luggage, which isn't too big, but seems reasonable. It's not as big as my big 85-liter backpack. So that's an introduction. And what we did was we took the situation, modeled it with volume. It was already in factored form, which allowed us to get an idea from our sketch of our graph how we should use our graphing calculator to set it up. Then to find the maximum, we had to use technology to figure that out. Yes?
Where did you get the length and the width?
I got the length and the width from my original diagram. So if I look at my original diagram, there's my depth, which is x. My length is x plus 10. So I added 10 to whatever number that I got for x. And my width was 90 minus 2x, or 100 minus the other two values, to get that last number. So let's look at example 1. Whew, lots of words. A piece of cardboard 30 centimeters long and 25 centimeters wide is used to make a box with no lid. You take squares, cut them out of the corners, and fold it up. So we have to imagine you have a piece of cardboard 30 centimeters by 25 centimeters, and you're cutting squares out of the corners. Can you see then, if after you cut those squares out, if you fold it along the red dotted line, you would get a box that would open like that. What are the dimensions of that box? What's the height? Here, Here I'll label, we cut out squares of sides x. So now we have to take this piece of cardboard with the squares cut out and transfer it to the dimensions of that box. Can you see that this height would be x? How long is this end here? The short end. Well, it was 25, but it's not 25 anymore. Minus 2x's, because we took x out of this and x out of this side. 25 minus 2x. And the long side, which was 30, is now 30 minus 2x. Part A, can we write a polynomial function to represent this volume? Volume equals length times width times height in no particular order. And then part B, let's graph this, and then let's talk about the domain. Well, in order to graph it, we could find, it's going to be useful to find our x-intercepts. Can you see that if you made it equal to 0, your x-intercepts are 0, 12.5, and 15? And so if I draw my axes here, actually, I'm going to have one at 0, one at 12.5, and one at 15. What kind of graph will this be? We have to figure out the end behavior. Is it going to be, why would you say an x to the 4? So if we multiply x by negative 2x times negative 2x, you will get positive or negative? Positive 4x cubed. So the end behavior will act like a line with a positive slope. So that means it's going to start from down here, go straight through, go straight through, go straight through, and end up there. What's the domain that makes sense? Okay, do negative volumes make sense? No. So is the domain only the place, again, we can label this as my volume. And this axis is x, which happens to be the height. If I went to my graph, the only part that makes sense is this section. Why doesn't it make sense to go past 12.5? I think it makes sense not to use negative values to cut out squares. I think we're good with that. But why can't I cut out a square of 13? It'll be too big. You see on the 25 side, if you cut out 13 on both sides, you're past 25. And that won't make any sense whatsoever. So our domain is that our x value has to be between 0 and 12.5. What's that? Yeah, you could do, now, in some textbooks, they'll include 0 and 12.5, because technically you could not cut anything out and have a volume of 0. Technically, you could cut out 12.5 and be left with a thin piece of cardboard that still has a volume of 0. But if you want an actual volume, you would have to go cut out something. So now that we've got our domain, we can go to part C and say, what is the maximum volume? So if this is the only domain that makes sense, we want to find that maximum volume. So I want to set up my window in my calculator to see that. Well, I'll type in the equation first. We had x times 25 minus 2x and 30 minus 2x. Go to my window. I know that my x values, maybe I'll go from -5 up to 15. And when I graph based on my old y values, it looks like my graph is going up way too high. So what I might want to do is go second table and look at my values. Now, my values on my table are already at 23 from the last time I looked at it. So I could hit the arrow up key for a long time until I get back to 0. The other thing, above your window button is a table set button, and you can get your table to start back at 1. So if you go table set and say table start at 1, you can go back to your table and it will start at 1. Between 0 and 12.5, it looks like 1500 is about as big as it gets. So when I go to my window,
Mr. Chair, how do you get to the table again?
so the table is by going second graph, because above graph it says table set. And there I can see that my maximum is looking around 1500. So when I go back to my window, I can set my y maximum value to be bigger than 1500 but close. So I went to 2000, and now when I hit graph, I can see that maximum value. So I can then calculate the maximum, choose a value on the left. I'll pick x equals 2. Pick a volume on the right. I'll pick 10. Yes, my maximum is between those two values. Push enter again. The question was asking, what size of square should be cut out? What is the maximum volume? What are the dimensions? We have to be careful because I find that the questions from this unit often ask multiple things in the same question. So if you only answer one of them, that can be catastrophic because there was 3 things to ask and you only answered one of them. So it asked for the max volume. The max volume is 1,512. Did it say to the nearest tenth? 0.0 centimeters cubed. It asks for the size of square. Well, the size of square is 4.5 centimeters by 4.5 centimeters, because that's your x. So again, looking back at your diagrams, you're like, oh, I labeled the size of my square as x. I've calculated x from that maximum point to be 4.5 centimeters. Now that I have that, what are the dimensions? 4.5 centimeters by 25 minus 9, 16 centimeters by 30 minus 9, 21 centimeters. And if you would multiply 4.5 times 16 times 21, you would get that maximum volume of 1512. Questions for practice are 3, 4, 5, 6.
What's the number after 4.5?
16, 9, and 10.